So let's start. So I'm Sathasivam from ICTVM, and this is week 5 of Introduction to Abstract Group Theory course. So the main topic that we are going to cover is symmetry groups. So we will do few examples computing the symmetry groups, and we will try to see some properties of it. So so here is the first problem. But before that problem, I will just recall the certain things that we have did earlier. Suppose if we have a symmetry group, let's say Sn, or probably we'll just take S4, and let's say if you have a permutation like this, okay? So symmetry group is basically a set of all bijection, right? It is set of all bijection from 1 to n to this set to itself. And the operation is via a composition of the maps. Okay. So suppose if you have a sigma like this, a permutation like this, where the sigma belongs to the S4, let's say it looks like this, something like this. Okay. Now what you can do is you can always, so by this permutation what it means is the 1 maps to 2, 2 maps to 3, 3 maps to 4, and 4 maps to 1. So when you have a permutation like this, you can always write it in terms of cycles. So you see where the 1 goes, this 1 goes to 2, and again this 2 goes to 3, right? This, so if you start with 1, this 1 kind of goes to 2, and if you look where the 2 goes, the 2 goes to 3 here. Okay. And again you look where the 3 goes, it goes to 4, and then now the 4 goes back to 1. So you can see it as some kind of cycle, 1, 2, 3, 4. Okay. So it basically, if you want to draw it, it looks something like this. Okay. Similarly, suppose you take another permutation like this, 1, 2, 3, 4, but here it maps like this. Okay. So now if you try to write it down, here 1 goes to 2, but 2 goes back to 1. And here 3 goes to 4, and 4 goes back to 3. So if you want, you can write it in like a cycle, 1, 2. So when I write like this, it means that 1 maps to 2 and 2 maps back to 1. Okay. Here this is 3, 4. Okay. So basically, if you have any permutation inside Sn, you can always give a cyclic decomposition. So this representation of this permutation is called the cyclic decomposition. Okay. So here in the problem, we have two permutation here. Sigma is a permutation and tau is a permutation. So the first question is to find the cyclic decomposition for each of the following permutation. Okay. So we have to find it for sigma, tau, sigma square, uh, sigma, tau, tau, sigma, and sigma square tau. So let's find it. So in sigma, if you look, you see that 1 goes to 3. Okay. So we'll first start sigma equal to the 1 goes to 3. And let's look where the 3 maps. 3 maps to 5. Right. So we have 5. And 5 maps back to 1. So this cycle is kind of closed. So let's take any other element. Let's say 2 here. 2 maps to 4. And here 4 maps to 2 again. So this cycle is also closed. So this is a cyclic decomposition of this sigma. Okay. But one can also see this is, you can also write it as 2, 4, 1, 3, 5. Right. Depends on which number you start. If you start from 2, let's say you will get 2, 4, 1, 3, 5. If you start from, let's say, 3, then what you get? 3 goes to 5, 5 goes to 1, and 1 goes to 3. So you'll get 3, 5, 1, and let's say 2, 4. Okay, so there are many ways you can represent this same permutation. There is not any unique way to represent it. So the cyclic decomposition in that sense it's not unique. But if you look here, what actually happening is you're actually we can change this order of these two disjoint cycles. So when I say two cycles are disjoint, the numbers are not written here. So for example, any number in this cycle will not appear in the cycle, and such a cycles are called disjoint cycle. So what you can observe is this cyclic decomposition is unique up to rearrangement of the cycle, and also you can inside you can cyclically permute. So if you have a cycle, inside the cycle you can cyclically permute, and here these two disjoint cycles you can permute in whichever the way you want. Okay, up to those kind of rearrangement, it is unique. So here you see what happens this and this. You're permuting this disjoint cycle to the front. Here what happens is you are permuting inside it cyclically. So it's not any random permutation. What happens is you're going cyclically, and then so so that is what happens. So if you want to see here in the diagram, see I can say 1 goes to 2, 2 goes to 3, 3 goes to 4. I can say like this starting from 1, or also you can start from 2 and you can say the same. So whichever the way you draw, it's the same thing. So up to a cyclic permutation, this cycle remains the same, but this disjoint cycle you can permute in whichever the way you want. Okay. So let's draw the tau. So let me have this here. So in tau, what happens is 1 goes to, so this is the tau. Okay, so this is the tau. Here what happens is 1 goes to 5. I erase it. And 5 goes back to 1. So this cycle is closed. Here 2 goes to 3, 3 goes back to 2. Okay, and the 4 goes to 4 itself. So sometimes you can just write like this, or you can just ignore it. If there is just only one cycle, you can just ignore it, and we can write in terms like this. Now let's compute the sigma square. Okay, so sigma square, what you can do is you can take the sigma here and then you can compute. For example, maybe I will write in both ways. You can do whichever the way you want. So this is the sigma, right? 1, 2, 3, 4, 5. Here what happens? 1 goes to 3. 2 goes to 4. 3 goes to 5. 4 goes to 2 and 5 goes to 1. Yeah. So you can check here. This is same thing. Okay, I think if I zoom out, I may not able to see it. So you can see here 1 goes to 3, 2 goes to 4, 3 goes to 5. So same thing I'm writing here. So this is the sigma. Now if you want to compute sigma square, what you can do is you do the sigma, you can probably will use different color here. Maybe this is not a good color. Sorry. So what I can do is I can send the sigma again here. So where the 3 goes to 5, right? So if you use the sigma again, 3 will goes to 5. What happens to 4? The 4 will goes to 2 here. And what happens to 5? 5 will go to 1. So you can see here. And 2 will goes to 4. And if you look, what happens to 1? 1 goes to 3. So basically sigma square is just this permutation. 1, 2, 3, 4, 5. So this 1 goes to 5. 2 goes to 2 itself. 3 goes to 1. 4 goes to 4. And 5 goes to 3. And if you want to write it in terms of cycles, what you get is 1 goes to 5. So you start from here, 1 goes to 5, and 5 goes to 3. Okay. Yeah, because 3 again goes to 1. So this here. So 2 goes to 2 itself, 4 goes to 4 itself. So I can just avoid those things. So this is your cycle decomposition of sigma square. Okay. But this is, it's a little bit hard. The advantage of writing it as a cyclic decomposition is that you can directly compute from here. So let's do that in that way also. So this is one way to do that. You just write it down and you can do. Now we can now try to compute it using the cyclic decomposition. Okay. So this is the sigma, right? So sigma square is nothing but you just write it twice. 135, 24, 135, 24. Now let's compute. Here we want to see, okay, usually the multiplication goes in this way. You have to compute from this side. So basically you need to compute in this direction, okay. Yeah. So let's try here. So what we are going to do is we are going to compute where all the elements maps. That's what we are going to do. So let's start with 1. Okay. And let's see where the 1 goes. So if you apply 1 here, this permutation does not change 1, right? So this 1 change 1 to 3. So now your 1 is going to 3. Now you look back, this permutation does not change 3. This permutation change 3 to 5. Okay. So this 1 basically goes to 5. Again, now we look at 5. This permutation does not change 5. This map 5 to 1. And here this goes 1 to 3. So 5 goes to 3. Okay. So now let's look at 3. This does not do anything to 3. Here 3 goes to 5. Here 3 will not, here 5 will remain invariant. Now 5 goes back to 1. So basically if you look, 3 goes to 5 and 5 goes to 1. So basically 3 goes to 1. Now let's look at 2. 2 will go to 4 and here 4 will go to 2. Right? So basically 2 will goes to 2. Similarly you take 4. 4 goes to 2 and but 2 goes back to 4. So 4 also goes back to 4. So this is nothing but 153. Okay. So you can check from here. So these two are the same. So advantage of writing in terms of this kind of cycle is that it's easier to compute it. You don't have to write it completely like this. You can write it shortly and then you can just compute. But there are something. See, writing in this kind of cycle has more advantage. We will see later why this is much better representation than writing something like this. Anyway, before going that, we will. Okay. Anyway, since I mentioned it, let me just point out what is the advantage, and then probably I will come back. I will do other problems, then we'll do it last. So, so this is one of the interesting property you can observe from here. So it says that the order of an element in Sn is equal to the least common multiple of the length of the cycles in the cyclic decomposition. Suppose if I have a sigma, which I'm writing it as R1, R2. I mean, okay, by R1 I means it's something like A1 to AR, and you have, let's say, B1 to, let's say, BS. Okay. And you want to look at the order of this sigma. The order of this sigma is nothing but LCM of R comma S. So that is what this particular thing says. And this is one of the main thing that we will prove today. But we will do something more. We have to come back. We have to use some other things, and then later we will prove it. But what you can observe here is if I write directly permutation, it will not help us. This kind of theorems will not come. So writing in terms of the cyclic decomposition helps you to directly say what is the order. Once you have the cycle, you just compute the LCM. But instead, if I write something like this, okay, in this way, suppose if I write here, I don't know. Okay, so that is a problem. For example, here I have cyclic decomposition. If you look at the order of this, you can directly say it's a order of this. It's a 3 cycle, so order is 3. You can directly say. But if you look here, I cannot say what is the order. So there are advantages in writing it as a cyclic decomposition. We will come back to this, but I just want to say that there are advantages. Okay, so let's move on to the next question. Okay, here we have done how much? So we have write the cyclic decomposition for sigma, tau, sigma square we have done. Let me probably just do the sigma tau, and maybe the rest of the thing we'll just leave it as exercise. Okay. So let's do the sigma tau. Okay. So what is the sigma? Sigma is nothing but 13524. Okay, so I have written the sigma here. We have computed it already. And what is tau? Tau is basically 1523, right? See, what we are doing here is, if you look here, this is also product of cycles, right? But this is not a cyclic decomposition. Why it is not a cyclic decomposition? Because this product is not disjoint. Okay, whenever I write as a cyclic decomposition, what we have is a product of disjoint cycle. But here, if you see, the 1 appears twice, 5 appear twice. So this is again you're writing as a product of cycles, but it's not disjoint cycles. Okay, so our aim is to write it as a product of disjoint cycle, and later I will tell you what is the advantage of writing it as a product of disjoint cycle. Okay, but right now let's write it as a product of disjoint cycle. So let's see where the one maps. Let's start with the same procedure. So one maps to, sorry, here the one is not there, so we don't have to worry. The one maps to 5. So when you compute, you have to compute in this direction. Okay, it's like the function composition. The function composition will always, if I write f compose g, I always first take g, then I take f, right? The same thing. So whenever I write the product is all actually composition. So you need to go in this direction. Okay, always remember it. You do in the direction of the composition. If you do it this way, it will not be correct, because we are defining it as a composition. Okay, so 1 goes to 5 here, and there is no 5 here, and this 5 goes back to 1. So what actually happens is 1 goes to 5, and then 5 goes to 1, so 1 remains like the same. Okay. Now let's start with the 2. So here 2 goes to 3, there is no 3 here, 3 goes to 5, so 2 goes to 5. And here 5 goes to 1, 1 goes to 3. Okay. Now let's look at the 3. 3 goes to 2, 2 goes to 4, and there's no 4 here. So this is 4. So this is, you can see here, this is a product of disjoint cycles. Okay, so the rest of the thing I'll just leave it as exercise. It's exactly the same. We'll leave it as exercise. So only idea here is basically you just have to go in this direction and just find it. It's not hard. Okay, so what we are going to prove next is that if you have a symmetric group Sn, this will be contained in Sn plus 1. Okay, so this first we will prove. Then from that, what you conclude is we'll conclude that Sn is a subset of subset of Sm for any m greater than or equal to n. Okay. So let's prove it. So remember this, what we are going to prove is Sn is contained in Sn plus 1. Okay. Well, this is you see, if you take a sigma here, write the sigma in terms of the product of distance cycle. Okay. So write it as some a1 to ar1 and b1 to br2, etc. Something you write here. Okay. Now what you can observe is all these numbers, these AIs, all of them belongs to the set n, right? So if you look here, all this set AI, BI, CI, all these elements that comes here, okay, all of them belongs to the set 1 to n, right? Because sigma is the element of Sn. So when you write, okay, sorry about that, internet got cut, I think. Okay, so I will just recall again. So you have a sigma and you write it in terms of a part of design cycle. Now you observe that all these elements, all of these elements are the elements of set 1 to n, because the sigma is contained in Sn. Sn means it's a permutation of n symbols, right? So it is only this, everything belongs to 1 to n. So in particular, what you can see is you can write a sigma, this same sigma, you can see it as inside Sn plus 1. Okay. How do you see it as Sn plus 1? Uh, See, what you do is these elements are the elements of Sn, right? Now you just add n plus 1 like this. Okay. So just add n plus 1 here. This means n plus 1 maps to itself. Okay. Now you can see this is this is some representation inside Sn plus 1. Okay. Or if you want, you can also see it in this way, uh, using Sn as a permutation. So let's say here is okay, probably I'll write in this way also. So sigma is a permutation, right? So it maps to some a1, a2 to an, right? So this is my sigma. How do you see it as an element of Sn plus 1? You see Sn plus 1 is what? Sn plus 1 is a permutation of n plus 1 symbols. So map this n plus 1 to n plus 1 itself. Okay. So this is now you can see the sigma as a element of, as a permutation of Sn plus 1. Okay. So whatever comes here, this sigma acts only in this way, and this S1 n plus 1 is kind of fixed. Okay. So thus, for any sigma belongs to Sn, so the sigma kind of when I say, probably I'll call it as a sigma prime, and this is the sigma. On this part, it's a sigma. On the entire part, let me call it as a sigma prime. Sigma prime belongs to Sn plus 1. Okay. Thus, Sn is a subset of Sn plus 1. And you can see it is injective. It's not hard to see it's injective. Okay. Okay, so we have Sn is a subset of, or if you want, we can rigorously write it. So how do you rigorously write it? So define a map F from Sn to Sn plus 1. Okay. What you do is you take this sigma and then just map it into, so, okay, I have to map it into, let's say, sigma prime, right? Now, if you want to map it into sigma prime, what I have to do, I have to define what is happening on the set 1 to n. right? Sigma prime is a map from where to where? It's a map to 1 to n plus 1 to itself. So how do you define this map? Sigma prime of x is equal to sigma of x if x belongs to the set 1 to n. Okay. And sigma prime of x equal to x itself if x is equal to n plus 1. Okay. So that is how you define the sigma prime if you want to write it rigorously. Okay. And then check this map is a, this map is a injective map. So if you want to say it is injective, what you have to say is you want to find the kernel, right? If so, f is injective is same as saying the kernel of f is just trivial. Okay. So let's find what is the kernel of f. So in this case, what is the identity? Trivial means here I have to write its identity. Okay. So what is this map? It maps x to x. Okay. So that is the identity map. So let's look at what is the kernel. Okay. So if suppose let's say uh, sigma belongs to kernel of f, so that means what? That means sigma prime is equal to 1, right? So sigma prime is equal to identity. So that is what it says. So sigma belongs to the kernel here, means if you map here, the sigma prime is identity. So sigma prime is identity means what? All of this place, when you write sigma prime of x, you have to get x. In particular, what happens to is the sigma of x has to be x for all x belongs to 1 to n. Okay. So this implies sigma of x is equal to x for all x belongs to 1 to n. Okay. Because when you say sigma prime of x is equal to identity, that means sigma prime of x is equal to x, right? But sigma prime of x is nothing but equal to sigma of x if x is in this set. So this tells you sigma is identity. So now we proved that this map is injective, and hence you can see Sn as a subset, as a subgroup of Sn plus 1. So when you see this Sn as a subgroup, the sets are different. Here is a bijection from 1 to n, and this is a bijection from 1 to n plus 1. But we are seeing via this homomorphism, we are seeing it as a subgroup. Okay. So when I say it's a subgroup, I see Sn as an image under this map, and then I call it as a subgroup. Okay. So basically, identify this sigma and sigma prime, then you can see it as a subgroup. Okay. So that proves the first part. So maybe I will do rigorously. This is just to give the intuition what we are doing it, but we will, whatever we did here is just we are rigorously writing it down. Okay, now we have done this. Now, how do you conclude? So, we need to conclude that Sn is contained in Sm for all m greater than or equal to n. Okay, so how do you do? So, what we have is we have Sn here. So, this is contained in Sn plus 1. This we have proved, right? And this statement we proved independent of this n. Okay, so now if you take Sn plus 1, what we have is this is contained in Sn plus 2. The same statement you use again. So this is the same statement, right? This n we doesn't fix. This is true. This statement is true for any n. So in particular, I can choose this as n plus 1. Then this will become n plus 2. Then you use the same thing here. This will be n plus 3. Okay. Now you can just go via induction. Okay. So now, the proof will go via induction. So probably we'll write the proof here directly. Proof by induction. Okay. So what we will prove is we will prove that Sn is contained in S n plus I for all I greater than or equal to 1. Okay. So this is what we will prove. Once you proved that, our statement follows, right? Because if you have m, this m is greater than or equal to n, right? So I can write, let's say I can choose I as m minus n. Okay. Then what is m? M is nothing but n plus I, right? So if I proved for any I, in particular it is true for this I also, and hence we are done. So it is enough to prove this statement. So this is the statement we are going to prove. So let's go by induction. See, this is just the intuition. Okay, but if you want to write a proof, it's you cannot just keep it like this. See, and hence it will keep on going. So if you want to write a proof, let's just write it, mathematically. So what you're doing is we just write it formally. That's all. So let's look at the base step. So the base step is where I is equal to 1. In this case, what we need to prove is Sn is contained in Sn plus 1. But this we have proved it anyway. Just earlier, just here we proved it. So now, assume that for I equal to k, Sn is contained in S I plus k, sorry, n plus k. Okay. We need to show. So this is the induction hypothesis. On the induction step, what is we need to show that it is contained in I plus k plus 1. Sorry, Sn is contained in Sn plus k plus 1. But how do you do that? So you have Sn is contained in Sn plus k. Now use this on this particular n. Okay. So this statement, this one is true for any n, right? It does not depends on the n. So that you have to be careful. If it depends on the n, you cannot directly do it. But this statement does not depends on n. So now instead of this n here, we see it as a n plus k, and then use this step. It will be contained in Sn plus k plus 1. Okay. So now by transitive, you got the solution. This. Okay. So and by induction, so since we got the induction step, so what now the proof follows by the principle of mathematical induction. Okay. So that is what we have. So the problem is we just have to say this is a subgroup of the bigger one. Okay, so let's move on to the next one. So here what we are going to show is Sn is non-abelian for all n equal greater than or equal to 3. So one way you can say is you take any n and then any n greater than or equal to 3 and then you find two elements in Sn. Uh, so that is one way you can do is let take any n. Okay, and what you do is you find these two elements, find the sigma and the tau belongs to Sn such that they does not commute. So sigma tau not equal to tau sigma. Well, this is also easy, but what we'll do is we'll just use the previous problem. So what we have is so we will go by contradiction, but you don't have to go by contradiction. This is I'll just use proof by contradiction. So in this case, we use by contradiction. So what we are going to do is we assume that Sn is abelian. Suppose Sn is abelian for all n greater than or equal to 3. Okay. So let's say it's abelian for some for n. Okay. So if you have a abelian group, what you can say about its subgroup? So the subgroup of abelian group is also abelian, right? Then what we have is any subgroup of abelian group. So then any subgroup is also abelian, right? So this we have. So what we here observe here, this S3 is contained in Sn for all n greater than or equal to 3. This follows from our previous problem. Okay. So in order to say that Sn is abelian, it's enough for me to say that S3 is sorry. In order to say Sn is non-abelian, it's enough to say S3 is non-abelian, right? Suppose if S3 is non-abelian, that gives a contradiction that every subgroup of that abelian group is abelian. Thus, Sn cannot be abelian, right? So, if what I'm trying to say is, if Sn is abelian, then S3 must be abelian. So, what we will prove is we will prove that S3 is non-abelian. If you prove S3 is non-abelian, that gives a contradiction, and hence Sn cannot be abelian. Okay, the contradiction occurs because you assume that you can directly prove it also, but you know. Okay, so let's prove that S3 is this we prove. Okay, so in S3, can you come up with the two elements? When you commute, they are not the same. So you have to come up with two elements, and then they will not commute. Okay, so it's easy to find such elements. There are many such elements. Let me take one element and see what happens. So let's see, we take 1, 2, and 1, 2, 3. Okay. I mean, how do you come up with this element? Just try a few elements, you will find one. Okay. Because this is S3, right? So the order is only 6. So you can just a few multiplication. If you do, you can always come up with some element. Okay. So let's compute here. What is this? This is 1 goes to. So here 1 goes to 2, 2 goes to 1. So it is 1 goes to 1. Okay. And what happens to 2? 2 goes to 3. 3 does not go anywhere. So it is 2 goes to 3. Okay. Here 3 goes to 1. 1 goes to 2. So basically 3 goes to 2. Okay. So let's compute the other way around and see what happens. So here 1 goes to 2 and 2 goes to 3. 1 goes to, sorry, 1 goes to 2, 2 goes to 3. So basically 1 will go to 3. Now what happens to 3? 3 is not here, but 3 goes to 1 here. So this 3 goes to 1. So let's close the bracket. Okay. Now let's look at what happens to 2. 2 will go to 1 and 1 will go to 2. So basically 2 will go to 2. Okay. So here if you observe, this is nothing but a 2-3 cycle. And this is a 1-3 cycle. You can see that these are not equal. Okay. So that means this element does not commute. Thus S3 is non-abelian. Okay. So this gives a contradiction. Okay, I will just mention the proof method again here. See, you can go via directly also. I'll just write a proof by contradiction just to give, there are many ways you can prove it. And so I'll just write contradiction. Okay. So if we want to prove that Sn is non-abelian, by contradiction, what we assume is that suppose Sn is abelian. Let's get a contradiction. Then what happens is any subgroup of abelian group is abelian. So in particular, S3 is a subgroup of Sn. So S3 has to be abelian. Okay. So what we have proved is S3 is non-abelian. So that means this statement is a contradiction to the statement that S3 is abelian. The contradiction occurs because you assume that Sn is non-abelian. Sorry, Sn is abelian. Okay. If you don't assume that, there is no contradiction. Since you assume Sn is abelian, that means S3 has to be abelian because it's a subgroup of abelian group. But we just proved that S3 is non-abelian. So it's a contradiction. So thus, this statement is not true. Okay. So Sn is abelian is not true. This Sn is non-abelian for all n greater than equal to 3. Okay, see, in fact, you can do it directly also. Inside Sn also, if you have Sn, inside Sn you take the same element again. Take 1, 2, and 1, 2, 3. So this is, let's call this as sigma and call this as tau. Okay, these sigma and tau are also again element of Sn, right? So all the other entries are fixed. Only one, it maps to 1 to 2 and 2 to 1, and every element is fixed. So this is again element of Sn, and tau is again element of Sn. So you multiply it, you will get the same kind of thing. So you can directly prove that Sn is non-abelian. Okay, so you don't have to go by proof by contradictions. I just wrote these few lines extra, but you don't have to write it. Okay, so let's move on to the next question here. Maybe before that we'll do this one. Okay, so here this one kind of tells you what is the advantage of writing the disjoint cycle. See, I can always write something like we just have observed. So I'm going for this problem because it's just related to what we did little bit before. See, if you write, these are two cycles, right? 1, 3, 2. Okay, so these are two. Sorry, 1, 2, 3. This is the cycle that we took in the previous problem. So what we have observed is this is not equal to 1, 2, 3, 1, 2. This is what we have observed. So what happens here is these cycles need not always commute, right? So the question is, okay, in which case I can commute it? See, why we care about commute is, suppose if it is commuting, our life will become easier. For example, if I want to compute, let's say power n, and if two cycle, let's say I have two cycle A and B, or maybe sigma and tau. Okay, suppose sigma and tau commutes, and if you want to take sigma tau power n, it is the same as the sigma power n tau power n, right? If it does not commutes, you cannot do it. If this is true, if sigma tau commutes. Okay. So it would be helpful for us to know when the sigma and tau commutes. So here you just now we have proved it that in general, if you take two cycles, it need not to be commute. Okay. But you can observe here, this one is kind of common. This 1 and 2 is common in both of the cycles. Okay. So this problem tells you that if you have two disjoint cycles in Sn, they always commute. Okay. So in general, it need not commute, but if you have disjoint cycles, it will commute. So let's say how you will prove it. So let me just take two cycles, and then I will try to prove it. Let's say you have a cycle, let's say sigma, I have written as A1 to AR. Okay. Let me call tau. This is nothing but B1 to BS. So when I say disjoint, that means this set A1 to AR intersection B1 to BS. This is empty, right? So this is the disjoint cycle we have. So what I have to write is I have to write sigma tau. Okay, and I want to say this is equal to tau sigma. Okay, so let's prove it. What is sigma tau? Sigma tau is just a composition, right? It's just A1 to AR, B1 to BS. Okay. So see here you observe that these are distant, but we are working with Sn, right? So basically, if you n 1 to n, let's say you take 1 to n, this 1 to n is nothing but you can write it as A1 to AR, B1 to BS, and let's say some C1 to CT. Okay, you can write like this. Why we can write like this? These two are disjoint, so these elements belongs to this set anyway, and whatever the set remaining other than these elements, there may be some elements remaining uh, in 1 to n, which is not these elements. Call them as C1 to CT. Okay. So now if you look at this CT, all the CIs, so if you look at the CI, this will be just CI, right? Why? Because you see, if you want to find what happens with the CI, see, there is no CI here. So if you start with the CI will maps to where? There is no CA here, but so this element does not do anything to CA. There is no CA here also. So this CAs will go to CA itself. Okay. So now if you look at, let's say you look at what happens if you write, uh, let's say we have A1 to AR and B1 to BS. What happens if you write AI? Okay. So this A, it will be something, it will be actually AI plus 1 or something. See here you observe there is no AI in this set because these two sets are disjoint. So this cycle does not do anything to AI. Only this cycle do something to AI. So there's a AI here and let's say AI plus 1 is here. So this AI will go to AI plus 1, right? So this will be AI plus 1. Or in, if you want, this is nothing but, this is equal to nothing but, so this is our sigma permutation, right? And this is our tau permutation. Because this AI is not inside this, if you apply the entire thing, this is nothing but the sigma of AI. Similarly, if you start with A1 to R, so and now let's say if you apply, let's say BI. Okay. Now what happens here? There is no BI here, so only in the tau there is a BI. So this when you apply it became tau of BI. Okay. So now what you do is you compute it the other way around also. Let's compute tau sigma also. So tau sigma I have to write in the other direction. So I think somebody joined right now. So I'll just mention quickly what we are actually doing. See, what we are trying to do is if you have two disjoint cycles in SN, we are trying to prove that it commutes. Okay. So we start with the two disjoint cycle A1 sigma and tau, which is two disjoint cycle. Disjoint means the symbols are the intersection is empty. Okay, and we are trying to see what happens with sigma tau and tau sigma. Okay, so we can write this 1 to n as a1 to ar, b1 to bs. So this element need not exhaust the 1 to n. So whatever remains, you write it as a c1 to ct. Okay. So let's compute tau sigma here. So sigma tau we have computed. Let's compute tau sigma. So this is nothing but a1 to ar, b1 to bs. So okay, in this let's see what happens to CA. CA will goes to CA itself, right? Why? Because CA is not inside any of this. If you take this cycle only permutes the elements which are inside this B1 to BS. Okay, so this cycle only permute these elements. It does not do anything to any other element. So since CA is not inside this and as well as this, none of this permutation do anything to the CA. So the CA will remain same. Okay. Then what happens to AI? Okay, so again call recall this is sigma, this is tau. Okay. So this AI is not inside this set. and this BA, this tau only permutes these elements, right? So A is not, since it's not there, only sigma will permute the AI. So this will go to sigma of AI. And if you take BA will go to, here in this case, BA will go to tau of BI, but tau of BA is again an element of B1 to BS, whatever the element it is, but that element will not be inside here. So tau of B will remain invariant under the sigma. Okay, so BA will go to tau of BA. So if you observe here, you can see that these two are the same. So this element maps to the same elements. So what we have is tau sigma equal to sigma tau. So actually the real idea what is happening is if you have a design cycle and when you are applying some element, uh, if this element is inside the cycle, then this cycle will act on this element. If this element is not inside the cycle, then it will not act on that. So if you have a design cycle, uh, it will act. So if you take AI, only AI will act. So whether this BA is in the front or BA is in the back, it doesn't matter, because AI only the sigma will act. And the BA also the same thing. Only the tau will act. Whether the sigma is in the front or sigma is here does not matter. Only the tau will act. Okay. So what we have proved right now is, if you write it as a disjoint cycle, then these things commutes. Okay, in general it does not commute. So here is the example we have, which is computed. So that is the idea, that is the reason. So whenever we have the cyclic decomposition, we always write it as a product of disjoint cycle, right? So when you go here we did the cyclic decomposition example. So here is the, in that particular problem, this is the sigma and this is the tau, and we compute sigma tau, and this is a cyclic decomposition, we are saying it, right? So one can ask, why not let's just keep it this way? Why do you want to go one step further and then reduce it in a product of disjoint cycle? Because if you write it as a product of disjoint cycle, these cycles commutes. For example, here sigma is like this, right? This cycles will commute. I can take this to this side also. But if you don't write it as a part of design cycle, this cycles does not commute. Okay. Okay. So let's move on to a different problem. So far what we have done. Yeah, this one we have done. This one. Okay. We will come back. So this is like the main problem of today's tutorial. This and the next one, but we will come back to that. So let's do this one. So right now we are just doing some small problem to get used to the notations, etc. And then we will come back to the real one. Okay. Now this one, find all the number n such that Sn contains a element of order n. Okay. So let's just do something. So what we know is what is the size of Sn? S7. This is actually equal to 7 factorial, right? Okay. So this is good. Now, what we know is by Lagrange theorem, if suppose x belongs to Sn, is 7, then what we know is the order of x divides order of S7, right? Which is equal to 7 factorial. So this much we know. But now the question is, see, divides 7 factorial, but that does not mean it can be any of the factor, right? So in general, the converse of the Lagrange theorem is not true. Suppose if you have a x which divides, if you have n that divides 7 factorial, there does not always exist an element x whose order is n. So in general, there does not exist such a x. So the question is, okay, so what are the orders for which there is a element of order n? So that is a question. So what we know is we know a little bit a partial converse of Lagrange theorem is known, which is the Cauchy theorem, which we have done this week. I mean week 5. So what the Cauchy theorem says? Cauchy theorem says the following: if you have a group G, okay, whose order is, let's say, n, okay, and suppose if P divides n, then there exists element of order P. So for random n, it does not need to exist, but what the Cauchy theorem says is, if the it is a P, if the P is a prime, okay, P divides n, and I have to also write a P is a prime, then there exists an element of order P. Okay, this is just there exists. Okay, so what are the primes that divides the 7 factorial? So the prime that divides 7 factorial, basically, okay, 1 is not a prime, but I'll just write anyway, 1 is also there. The identity element has order 1. So 2, 3, 5, and 7. Okay, so there are the elements in this order. So that just comes by Cauchy theorem. Okay, maybe I have to move it here, and maybe just erase this. Okay, so this one is just identity. The rest of the things will. So this one is just take this identity. Okay, so this has order 1, and the rest of the things comes from the Cauchy theorem. Okay. Now the question is, okay, what are the other n that is possible? Okay. So what we do is, let's take any sigma here. Let's compute it. So here now, in general, if you have a problem like this, it is not easy to answer, right? If you are seeing your permutation like, let's say 1, 2, 3, and then you are going a map like this, 2, 3, 4 or something. Sorry, 4 here, maps to something. Like this you are doing. From here, it's not easy to see what is the order. But if you write it as a part of disjoint cycle, then you can actually write. So let's say you take a sigma, okay? Now the sigma, I can write it as a part of disjoint cycle, right? So let me look at what are the cycles that are possible, okay? So I'm writing as a, let's say we have some cycles. Let's say the first cycle, so it is a part of cycle like this, right? This length, R2, R3, Rn. Okay. So what is the length? So length of the cycle A1 to AR. This is nothing but R. So how many elements are there? That is what I called as length. Okay. If the length of this cycle is R1, R2, something like this. Now, okay, now we are saying, okay, what are the length that is there, that are possible? Let's say if your sigma has a length 2, one cycle of length 2 is there, okay? So the totally how many elements? You have 7 elements. Let's say there is one element of length 2 is there, okay? So then how many other elements? There are 5 remaining elements are there. In the 5 remaining elements, you can have a, see, if you have another 2 cycle, you can have. If you have another 2 cycle, the order is kind of, okay, probably what I will do is I will, okay, I will just tell this, we will use this property, then we will prove it, okay? So we might need this property. So when we do the example, we understand why we need that property, then we will come and prove it, okay? So what it says the following: if you have a, prove that the order of element Sn is equal to the least common multiple of the length of the cycle in its cyclic decomposition. So what it says is the following: if I have sigma, which is written as a product of cycles, okay? Let's say this length is R and this length is S, okay? It's a product of disjoint cycles. Then if you look at the length of the sigma, sorry, the order of the sigma, The order of the sigma is nothing but LCM of these numbers R and S. If you have something like a C1 to CT, okay, then your length will be, there will be T coming here. So you take the LCM of that. So for now, let's just assume this particular statement. Okay. So assuming the statement, let's try to prove what is the length. Oh, it's okay. What are the possible thing we can put? See, we can put another 2 cycle, but then if you put another 2 cycle, the LCM will not change, right? So we will look at things where the LCM actually change. So you can put a 3 cycle here. If you put a 3 cycle, then how many elements will be there? There are 5 elements already there. So this is a 5 element. There is a two elements. Two elements can be written as a either a 1 cycle or a either 1 cycle, or it can be written as a 2 cycle. Even if you add a 2 cycle also, say something like 2 cycle also, the LCM of the order does not change. So LCM of the length does not change. So it doesn't matter if you put a 2 cycle here or not. Okay. So now let's look at 2. What are the other possibility I can put? I can put a 5 here. So there are 5 more elements. I can put 5 more elements. Okay. So here I just want to repeat it again. There can be 2, 2, 3, 1, something like this. Okay, 2, 2, 3. This is also possible. But if you see, if you look at the order, which is the LCM of 2, 2, 3, this is the same as LCM of 2, 3, right? Because this 2 twice repeat does not actually matter when you do the LCM. So that's why I kind of ignore this, and I will just write it down. You can write it down if you want, and then look at all the order. That is not a problem. Okay. So this is the only possibility when you have a one of the 2 cycle. Okay. Let's say 1 cycle is a 3 cycle. Then what are the possibilities? The only possibility is that you can have another 3 cycle you can put, or you can put another 2 cycle, right? Some combination of 3 cycle and 2 cycle is all you can put, because 3, that means you have 7 elements total. You are working with S7. Already 3 elements are gone, so that means you have remaining with 4 elements. So you can put a 3 cycle and a 1 cycle, or you can put a 2 cycle and a 2 cycle, in whichever the case, or you can put a 2 cycle and a 1 cycle and a 1 cycle. So in whichever the case, you have already observed it already. Okay. There is a 3 and there is a 2, and that is already done. Okay. So this possibility is there. Other than that, whatever comes, we have already calculated. Okay. Now what about 5? With 5, you can leave just 5, or you can put 5 and then you can put a 2 cycle. Okay. So these are the possibilities. But here you can observe, let's compute the order. Order here is the LCM of things, right? LCM of 2 and 3, which is equal to 6. Here the LCM is 10. So let me call this a sigma 1, sigma 2, sigma 3, sigma 4, sigma 5. So this you compute the LCM, you will get this is equal to 10. This is 3. So this is again a 10. Okay, I think I might have missed a few. See, what we have put is we have put a 2 cycle, we have put a 3 cycle, we have computed. Then we can also put another, right? See, and I went directly to 5 cycle, but you can put a 4 cycle also. So I will erase this part. We'll just erase these things. We'll come back, we'll write it down. See, I can put a 4 cycle. If you put a 4 cycle, what are the other possibilities? There are 3 elements you can write. So there can be a 3 cycle. Okay. Or there is another possibility. So you can write a 4 cycle. You can write a 2 cycle. And then 1 cycle. So this is also possible. Okay. And another thing that is possible is just to put a 4 cycle. Okay, but you can see this both has the same order. So in some sense, you can either take this or take this. You don't have to take both of this. Okay, so just in that sense, I just take it out. Just there's a 4 cycle I will put again in the below. I mean, of course, you put all the cycles, all the composition you put, and then avoid the ones that are repeated already. And I can also put a 6 cycle, right? 6 and then 1. So this is also a possibility. So I started with the 2 cycle here, 3 cycle I can put, 4 cycle if I put, 5 also I have, 6 I also have. So these are the cycles that are possible. Of course, we can do other ones like, as I mentioned, you can put something like another 2, but the LCM remains the same. So, so here's a 6, and here is 10, here is 3, and here is 5. Okay, this is also the same thing as this, right? So this also doesn't really matter. So this also I can take it out. See, we are just looking at the possibilities where the LCM kind of comes differently. Okay. So 4, 3 is 12 here, 4, 6. Okay. So what are the possibility here? We have 6, 10, 3, 5, 12, 4. Okay, and but anyway, 3 and 5 we have already seen there is a possibility. What are the other possibility? 1, 2, 7. So add it to this. So you'll have 1, 2, 7. Okay, here also I can just start with the 2 cycle if you want. Okay. 1, 2, 3, 5, 7. Okay, 6 is also there, right? So 6, 7, 12. Okay, of course 4 is also there. So these are the only possible elements. The only possible order for the elements. The other orders are not possible. Okay. If you look at S7, S7 is a big group, right? But for example, S7, if you look here, so if you look here, order of S7 is 7 factorial. So for example, something like 3 times 5, which is 15. 15 also divides 7 factorial. But you can see here, there is no element of order 15. So in our element of order 15 does not exist here. Okay. So these are the only possible orders. So how do you do is you just use this property. So okay, here I skipped a few cycles, but because if you write all the cycles, it became lengthy, so I skipped it. But if you want, you can always write. For example, 2 cycle, I will just write every possibility. If you want, you can do all of these things. So if you want to write for 2 cycle, this can be a 2, and rest of this is 1, 4, 5. Or I can write a 2 cycle, 2 cycle. So how many 2 cycle is there? 2, 2, 4. So these are all possibilities, right? But all this possibility, I just write only this one, because if you take all of this, the LCM is kind of the same as 2. So this possibilities I kind of skipped it. If you want, you can write all of this, and then you can say, okay, what are the order? If you look at the order is 2 here, order is 2 again, order is 2 again, and you can do all of these things. In this case, I kind of skipped many of those things and just write one which actually gives you different orders. But here also, if you even if you do that, also you can observe that 6 comes kind of twice. Okay. But anyway, if you want, you can write all of this. It's not very hard, but uh, for this 2 you write, now 2, 3 also you have to write. It will take some time. You can write and you can compute. But what we did here is, once you have that one cycle, we are kind of avoiding all the same cycles. So what are the other cycles you can put? You can put a 3 cycle, but then this became 5. Then whatever the cycle you can put again is just a 2 cycle, but that we will ignore it, because already a 2 cycle appear. So you have 2 cycle and a 5 cycle. And another thing what you can put, 2 and 5 is already 7, so there you cannot put any other cycles. If you start with the 3 cycle, you can just keep a 3 cycle, or you can put a 2 cycle, but that is same as this one. Okay, if you think you can put a 5 cycle, you cannot put a 5 cycle, because otherwise the elements, the total number of element you need is 8, but you are working with S7, so you cannot do that. Okay, of course you can put another 3 cycle, another 3 cycle, etc. But okay, another 3 cycle and 1 cycle, something like this. But this is the same as the LCM is finally coming same as 3. So we are trying to put some other number. We are not trying to put the same number. Okay. So this 2 you can also put 4 also. Something like that you can put. But that 4 you can compute again. Anyway, so it's up to you to see how you're going to put, but finally you just compute all the different ones, all the different possibilities. The best way is, of course, write everything down. Okay, that is the best way, but that will take a while. So the easiest way is whatever you put here, don't put the same thing again. Look for everything else that you can put. You put a 2, right? Don't put 2. What you put, you can put 3, you can put 5. So you can put 3, you can put 4, you can put 5. Well, you cannot put 6 because otherwise the elements, you need 8 elements. So now you have 2, 3, and let's say you put 4 also. Okay. Now you start with the 3. 3, if you cannot put 2 because that is already counted above. So 3 and then 5 also is not possible. And then you start with the 5, and then what are the possibilities? And then you go to 6, what are the possibilities? Okay. So like that you can try to count. Okay. So you put one cycle, one of the cycle, and then see what are the other possible cycle which are kind of different than this same cycle. Okay. So what we have proved is the Cauchy theorem you cannot generalize. That is the one thing we have shown. So Cauchy theorem says if you have a prime that divides, then there is an element of that prime order. But in general, it's not true if you have a composite. For example, if you have a, let's say 15, there is no element of order 15 in S7. Okay, so we have done some of this. So let's now directly go and try to prove that particular problem. So we have used that LCM property, right? So that is one of the interesting reason that we are doing the cyclic decomposition. When you do the cyclic decomposition, the order of sigma can be easily written down. So this is what I was trying to say here. So this is the particular statement I am repeating. The reason we are writing it as a part of design cycle is you have a property like this. If you want to find the order of sigma, you can easily compute. Otherwise, if you write in that arrow like function kind of representation, it's almost impossible to find. I mean, it's not impossible. You just have to compute it, but it's very hectic to compute it. So by writing in this way, it became easier. You just have to compute the LCM. Okay. Anyway, so let's try to prove it here. This is our main property to prove. Before proving that, we needed one more problem. Once we have that, we can prove it. So let's prove this particular one. See, I think I should have gone one question after another, but I'm just moving up and down. I'm sorry about that. Next time I try to organize it properly. Okay. So let's try to prove this particular question now. So the question says the following: if sigma is a M cycle, then M cycle means A1 to AM. Then for all I in 1 to M, sigma power I of AK is AK plus I. Okay. Where you write K plus I replaced by mod M. So basically, if you have something like a K plus I, you write it as okay, I probably will write here. Suppose you have a cycle like this. Let's say 1, 2, 3. Oh, maybe A1, A2, A3. A1, A2, A3. Okay, so this is the sigma, let's say. If you want to find what he is telling is, so here if you observe what happens, 1 goes to 2, 2 goes to 3, but you see 3 where the 3 goes. 3 goes to, it's not goes to 4, right? So if you write like this, take the I as 1, okay? So what this statement says is sigma of AK maps to sigma of AK plus 1. Okay, when I is equal to 1. This is the statement that we have. But if you observe here where the 3 goes, 3 does not goes to 4. See, 3 goes to A1. Okay, so that is same as telling A3 goes to A3 plus 1 mod 3. 3 plus 1 is what? A4 mod 3. What is 4 mod 3? 4 mod 3 is 1. Okay, so that is what he is trying to say. Once you go beyond this, you just look at the remainder back. Okay, go back. That's why you take this mod. So let's say our sigma is so basically what happens is if you take a sigma, it will go one step, one step, one step, and then m will come back to here, and yeah, and then it will kind of rotates again. So that is what happens when you have a I equal to 1. If I equal to 2, then what happens is 1 goes to 3, like, so you have a1, a2, a3, a4, something like that. If let's say sigma square you are applying, in this case sigma will take here and then sigma square will take here. So basically if you do sigma square, you totally go from a1, you will go directly to a3. Okay, and then from a3 you will go to here and then one step down. So basically from a3 you will go, okay, so if you take a3, a3 will go here and then this will come back here, right? So basically it goes two step down. Okay, so a4 if you go, it will also go two step. So two step is same as going 1 2. Okay, so it's basically 6 mod 4, which is 2. Okay, so let's try to prove it. Okay, so here what happens to suppose if this is my sigma, okay, if I apply sigma to let's say ak, then what will happen? Sigma to ak if you apply, what happens if it is a if suppose my k is less than m, okay, strictly less than m. Okay, so basically k is not in this end term. Okay, then what happens? It goes to ak plus 1, right? So if you it is there, let's say 1 is there, it goes to 2, 2 will goes to 3, because that is how this thing happens, right? And ak, so okay, probably I have to write it properly. It's equal to this. It's equal to a1 if k equal to m. So this is what we have. This is what this sigma will do. Okay. So if you have m, it will maps to 1. Otherwise, it will just go one step forward. So this one, I can, I can kind of change it like the following: ak plus 1 if k is less than m, or I can write it as ak plus 1 mod m if k is equal to m. If k is equal to m, this will become m plus 1, right? M plus 1 mod m is nothing but 1. So that is what we have here. Okay. So now here, if you look, k plus 1 in this case is less than or equal to m, right? So, so what I can do is I can just write it as the above also. I can write it as uh, ak plus 1 mod m is less than. So in both cases, I can just write it like this. Okay, just one small thing. Okay, so what we have is k plus 1 mod m if m is if k plus 1 is greater than m. Okay. Only in that case we are going mod m. Otherwise we are not going mod m. Because if you have m here, let's say k is k minus m minus 1 or something. Let's say k is m minus 1. So this became am, right? If you go directly mod m, this will become a0. But you see I have no a0 here. So there is a1 to am, not a0. So that sense it's a little bit different. It's not any different, it's just the same thing. But instead of usually in zm you will take 0 to m minus 1, right? In this case they are just taking 1 to m. But if you look at this, m is actually the 0 here. But anyway, so this is what we have. This is for sigma we have. Now what we have to prove? We have to prove for all sigma I. How do you do? Proof goes by induction. Okay. Assume for I equal to k. Is I not I equal to k? So okay, I will write I equal to n. We have sigma power I of a k is nothing but a k plus I mod m. Okay, maybe I will just write it a little bit different. Okay, maybe it's fine. A k plus I mod m if k plus I is greater than I. Okay, otherwise it is basically a plus k plus I if k plus I is less than or equal to m. So that is what we are having for the induction statement here. Sorry, base step here. For induction also, induction hypothesis also, we assume this. For n, we will assume this. Okay. Sorry, a power n, right? It's not I, this is n. Okay. So this we have, these two we have. Now we will do one more thing. What we have to look at, we have to look at the sigma n plus 1 of ak. But sigma n plus 1 of ak is a sigma of sigma n of ak. This is nothing but sigma of a plus k plus n plus 1. Sorry, a plus k plus n. Now apply the sigma again. It will be sigma of a plus k plus n plus 1. Okay. Sorry. But only problem is both case we have this mod formula. If the k plus I is greater than m, then we will go, let's say, we'll go mod that. Okay. So the same thing comes here also. So this is same as ak plus n plus 1 mod m if k plus n plus 1 is greater than m. Okay. Otherwise, it's the same element. Okay. So the mod statement to follow directly from this particular one. For the base step, what we did, the same thing. So this particular one, we will do the same thing here. Okay. So by induction, then the proof is done. Okay. So this one we have done. So basically, what it says is you are just going cyclically. If you have something like a1, a2, a3, a4, a5, let's say a6, and this is, let me call this as a sigma. This is a sigma. If you have going to sigma square of, let's say you go a2, this is nothing but go 2 at a time. Okay. So sigma moves everything once, right? So sigma square kind of moves everything twice. That is what basically this statement says. It does not say anything really big, although it looks like there is some mod etc comes, but basically it says sigma square is same as going twice. So that we anyway know. So if you do A2 of sigma square, it goes to A4. That's what it says. Okay. So that A4 I can write it as A2 plus 2. That is what it says. Okay. Using this, what we now prove is let M be a M cycle 1 to M, so that sigma power I is also cyclic if and only if I is relatively prime to M. Okay. So now this statement we have to prove. Let's see how we can prove it. Okay, before that, we still haven't proved this part, right? So what here we have is deduce the order of the sigma is M. Okay, so let's prove this again also. So I want to prove that order of the sigma is also M, right? So first of all, what we can observe is if you go sigma power M of, let's say, it start with any AK, this will be nothing but AK plus M, right? So here you observe that K plus M is kind of greater than M, so we go mod. So this is nothing but AK, basically it's AK. Okay. So this will be AK plus M mod M. Okay. So once you go more than M, you always come back. So this is basically the cycle here. When I say 6, so you go 6 is same as if you go in this direction 6, 1, 2, 3, 4, 5. Okay, if you, let's say you go in this direction 7, 1, 2, 3, 4, 5, 6, 7. Going 7 is same as going only one time. Okay, because the cycle length is 6. If you want to go 7 times, so 7 steps you move in this cycle is same as you are moving only one step, right? So that is what we are using here. Going K plus, okay, where is this? Going K plus M is basically same as going K plus M mod M. So this is nothing but AK. So what we have observed is the order of sigma divides M. Why? Because if you take any to the power M, this is the identity, right? So it's basically what it says is sigma power M is identity. So order of the sigma divides M. Now let's say this is M is the smallest one. If you want to say something is the order, what I have to say? I have to say that is the smallest number, such that sigma power M is identity, right? So let's prove that this is the smallest such number. Suppose if I is less than M, okay, then consider this one, sigma power I of A1. What is this? This is nothing but sigma of I 1 plus I. Okay. Now look at what happens with 1 plus I. Depending on that, we go either mod or not, right? So this will basically become 1 plus I. Depending on that, we'll go either mod. Whether we go mod or we won't go. That depends on that. If you look at 1 plus I, what happens? So I is strictly greater than M. Okay. So that means I is less than or equal to M minus 1, right? So if you go by I plus 1, so this is same as here, 1 plus I. This is less than or equal to M. So we will only go mod when uh, the number you got is greater than M. So in this case, it is less than or equal to M. So this number is the same. Okay. So this one is not equal to AI. Okay. So basically this number here. So we won't go mod. So this is the correct one. Sigma I of A1 is nothing but A1 plus I. Okay. Now, if you apply this A, if you look at this A 1 plus I, this A1 plus I is not 1. Why? Because A1 plus I is one of the element here. You have element A1 to AM. A1 plus I is somewhere here. Somewhere here. So what you're doing is every time you go like this, if you come reach to 1, and if you go further, the further you go like this, right? In this case, the AI is somewhere in between. So these elements are all different. Okay. So this is not equal to A1. So what we have proved is sigma I is not identity. If sigma I is identity, then it has to take A1 to A1, but in this case it does not take A1 to A1. Okay. Because AI plus 1 is one term here. So you will go to A1 again if you reach AM and then go back. Okay, so these elements are all distinct. These elements are not same. When I write this a product of design cycle, these elements are all distinct. So the only way I can come back here is after I reach AM and then I go one more step. But in this case, what happens is you will not go that much. You will go less than or equal to M. So this is what it says. Okay. So that means sigma I is not equal to identity for any other I less than M. So M is the smallest such number. Thus order of M is thus order of sigma is M. Okay. So in particular, what it says is if you look at the subgroup generated by sigma. Okay. So what is the subgroup generated by sigma? This is nothing but identity sigma, sigma square, etc. Basically sigma power m, right? Sigma power m is basically identity. So this group has order m. That is what it says. Okay, keep that in mind. Let's come back to the next question. So the next question says, suppose m is sigma is a m cycle like this, and sigma power I is also a m cycle if and only if I is relatively prime to m. Okay, so this is what it says. So this is a statement you might have studied in cyclic groups, right? When a thing is again a generator. See, if inside this group, okay, you remember this statement, we will try to prove it. It says sigma I is also m cycle if I is relatively prime to m. That is what it says. So where is this? So here you have a sigma. So what it says is if you take sigma power I, this is also M cycle. M cycle means what? It is also a generator, right? So any time you got a M cycle, the order is M, so it will be a generator. So what it says is if that is also a generator, okay. If sigma power I is also a generator, if and only if this I is congruent to, sorry, if I and the M are these are coprime. Okay. So that is what it claims. Okay, so how do you prove it? So one of the easier way to prove it is to, one can directly prove it, but easy way to prove it is give a isomorphism, because here you observe this has order m, right? That means this is actually what, this is isomorphic to Zm, that we know because this is a cyclic group. So give isomorphism to Zm. How do you map? You take the sigma, map it into 1. Okay, so this is isomorphism. Here you can observe this is a generator of this group. This is a generator of this group. So you have a map like this. And both has order m. So this is a homomorphism. So this defines a isomorphism. How do you do? If you take sigma power n, map it into n. Okay, so 1, map it into n. Okay. Or sigma power I, map it into I. So if sigma power I is a m cycle. Okay. Okay, in particular, I want to say that all the sigma power I need not to be m cycle. Okay, let me just give an example to say that it's not in general true. For example, you take 1, 2, 3, 4, okay, and then you just square it. This is nothing but 1, 2, 3, 4, 1, 2, 3, 4. Let's compute it. This will be 1 goes to, see here, 1 goes to 2, 2 goes to 3, so 1 goes to 3. Okay. I mean 1 goes to 3. Now let's look. 3 goes to 4, 4 goes to 1. So this will be closed. And you take 2, you can observe that 2 goes to 3 and 3 goes to 4, and this is actually this one. Okay. If you observe here, this is not a 4 cycle, right? And this order is also not 4. The order is 2. If you remember whatever we have it. So this is not a 4 cycle. So when you square it, it need not to be a 4 cycle. So sigma power I need not to be m cycle. So what it, if sigma power I is a m cycle, okay, I'll just erase it. If sigma power I is a m cycle, then what we know is a sigma power I is a generator. Okay. Sigma. Okay. So now we have isomorphism here, right? So the isomorphism is, let me call it as F. So under the isomorphism, generators maps to a generator. So thus f of I, sorry, f of sigma power I, which is nothing but I, is a generator. Generator of Zm. Okay. So in Zm, we know when an element is a generator, right? So in Zm, so if you take a x, if x is a generator, if and only if this statement we have, what we have, x comma m is equal to 1. So x and m are co-prime only, it will happen. Thus, since it is a generator, what we have, the I is a generator in Zm, what we can conclude is GCD of I comma m is nothing but 1. Okay. So that is the statement that we want to prove here. Let's go quickly and say. So it is a m cycle if and only if I is relatively prime to m. GCD relatively prime means the GCD is 1. So of course one can directly try to where I wrote it here. Yeah, here one can directly take this group and then you can try to compute everything again. But see, we know that for cyclic group that is the thing, right? So in that sense, we can just go via isomorphism and then you directly cut it. That's all. So it's an isomorphism. So let's come to the main problem here. So this one we will do. I'm not sure. See, if you prove the 15, the 14 will kind of become a consequence. Okay. So I took this from some book, and in that book, what happens is they're kind of motivating the 15. So what the 14 says is the following: if P be a prime, so that the element has order P in Sn, if and only if it is a product of commuting P cycles. So this will become a consequence of this problem, but they kind of motivate this particular problem. But what we do is let's directly prove this, and we use this to prove the 14. So let's try the 15 one. Okay. So the question says the following: prove that the order of an element in Sn is equal to the least common multiple of the length of the cycle in its cyclic decomposition. So let's take a sigma belongs to Sn, okay, and write the sigma as the product of uh, cycles. So we'll just look at how we can write it as specific. So you write it as A1 A2, etc. AM1. Two. And maybe I'll just directly write K here. And then maybe K minus 1. Okay. Okay. So now it's a product of K cycles. Okay. In fact, this MK is actually equal to S. Okay. That is also you can write. MK is basically S. Okay. Maybe it need not to be S because there can be some other elements like one cycle can come. Okay. This we have. Right now, what we have to prove is and the order is basically the least common multiple of its length, right? So that is what we want to prove. So basically what we have claim is nothing but the order of sigma is nothing but LCM of M1. Okay, maybe I will write. Okay, sorry about rewriting it. So this is usually how people write the cycle, but for us it's not a really good idea. So I will just write it a little bit differently. So I will write it as a A1. Sorry, A1, A2, AR. Let me write. Okay, if I write like that, I cannot use enough symbols. So C1 to C2 to CR3, etc. I'll just put that like this. See, I can write it using two subscript I have to use, but I don't want to use two subscripts. So let's just work with this one. Okay. I don't want to go in the notations. Rather, what we do is we'll just prove for this particular one. Okay. In general, what you do is instead of writing A, so the problem here is if I write A, B, C, then I will stop at some point, right? So if you want to write in general, what you have to write it as something like this. You have to write it as product A1, A1 or AI1, AI2, etc. AI or I. You have to write something like this. For I run from 1 to T. Where T is the number of cycles. Here in this case, I have 3 cycles. Okay. So you have to write something like this, but I don't want to use this kind of notation. So let's just stick with the 3 cycle. Okay. For now, let's just stick with 3 cycle. We just try to prove only for 3 cycle. Only for 3 different cycles. It can be anything. The proof goes same, but you just have to use this notation and then you have to do exactly the same. So what we claim is the order of sigma is nothing but LCM of R1, R2, R3. Okay. So this is what we are claiming. So let's prove it. So what we want to prove, we want to prove. Let me call this as alpha. Okay. So what we want to prove is the order of alpha. Maybe let's not introduce new notation. Let's just use the same notation here. Okay, I think somebody came, so I uh, just mention what is the thing we are trying to prove. See, what we are trying to prove is if you take an element of Sn and write it as a product of disjoint cycles, okay, you write it as a cyclic decomposition. Then the statement that we want to prove is the order of this one is nothing but the LCM of the length. So this has R1 elements, this has R2 elements, this has R3 element. So the order is basically the LCM of the length of each of the cycles. Okay. So that is what we want to prove. So in order to prove that this is the LCM, what we have to say is, we have to say first, we want to say this is equal to 1. This is the first step we want to prove. And we have to prove that this is the smallest such positive number such that the LCM is equal to 1. Okay, so that is what the thing that we are going to prove. Okay, so let's prove it. So this is the first one, and then the second one is the least n such that when I say least n, I say least n belongs to the natural number such that sigma power n is 1. In that case, 1 is the identity. Identity is basically, the permutation which takes the element to itself. For example, 1 goes to 1, 2 goes to 2, 3 goes to 3, etc. So this is the identity permutation. When I write 1 here, it means identity permutation. So let's prove one by one. Let's prove the first step. Okay. So we have, let's see, this is our sigma. Okay. So let me call this as maybe sigma 1, sigma 2, sigma 3. Just for the notational sake, sigma 1, sigma 2, sigma 3. Okay. So sigma is nothing but what? Sigma 1, sigma 2, sigma 3. Okay. So now I look at the sigma power LCM of R1, R2, R3. Okay. So this is nothing but sigma 1, sigma 2, sigma 3 power LCM of R1, R2, R3. Okay. But here we have proved one statement, right? If you have a disjoint cycle, it commutes. So I can commute these things if I have a disjoint cycle. Okay. If I don't have a disjoint cycle, I cannot commute. But when you do the cyclic decomposition, you will always get a disjoint cycle. So what I can do is I can commute these elements. So if you can commute these elements, then what happens is this LCM I can take inside. So if A and B commutes, if AB equal to BA, then what happens is AB power n, this is nothing but A power n, B power n. We have this identity if they commutes. So in this case, since this sigmas commutes, because they are disjoint cycle and it commutes, which we have proved it, this LCM I can take inside. So this is nothing but the sigma 1 of LCM of R1, R2, R3, sigma 2 of LCM of 3, and then we'll write sigma 3 of LCM. Okay, so since this is a LCM, what you also know is R1 divides the LCM. Okay, R2 also divides the LCM of this 3 number. R3 also divides the LCM. Okay, so what is the order of sigma 1? You look here, this is a R cycle, R1 cycle. So order of this is basically R1. This also we have proved it, right? That particular, before we have proved this statement. Well, yeah, see this one we have proved here. Okay, if you take a M cycle, then the order of the sigma is nothing but M. This we have proved. Okay, so this order is R1, but then R1 divides the LCM, so this will become 1. Okay, so what we have proved is we have proved the first step. Now what remains is to prove the second one. We want to prove that this is the least number. So let's try to prove something is the least number. Okay. So again, assume that this sigma is sigma 1, sigma 2, sigma 3. Okay. Suppose we have n such that sigma power n is equal to identity. Okay. So this implies what? Sigma power n is n is nothing but sigma 1 power n, sigma 2 power n, sigma 3 power n. Why? Because these elements commutes. So I can write. And this is nothing but identity. Okay. So this is identity means what? All of this has to be identity, right? Because you observe here, these are all disjoint cycles. So whatever this only acts on A1 to AR, and this only acts on B1 to BR, and this only acts on C1 to CR. Okay, so if you take A1, this things does not do anything to this A1. Okay, if you take a sigma of A1, this is nothing but sigma 1 of A1 or sigma of AI, any AI you take. Okay, sigma 1 of AI. If sigma power n of AI is equal to AI, that is what it means by identity, right? So this one also has to be AI. So this things also has to be identity. Okay. So that means this is identity, and since these things are distinct, what we can prove is sigma 1 power n, so sigma I power n is equal to identity for I equal to 1, 2, 3. Yeah, all of these things are identity separately. But what we know is Ri is the order of sigma I, right? But what we know is this n also has a property that sigma I power n is equal to 1. But this is the order. That means this is the smallest thing. Now use the Lagrange theorem. It kind of tells you that, not Lagrange theorem. This is just a property of cyclic group. So from here, what we can observe is that this Ri divides n. Okay. So this is just a property that you know from the cyclic group, right? If you have a element A power I, and let's say A has a order n. So order of A is okay. This is just a property, you can easily prove it. Suppose if order of A is some n, then if you have A power I, this order is nothing but not A power I. Then A power I is nothing but A power I mod n. Okay. So this is just a property of cyclic group. You can easily prove it. And from here, it directly follows. Okay. So that means what happens is that this from this one, if you are using it, what you will get is n is congruent to Ri mod n. So that means n is what? 0 is congruent to Ri mod n, right? That is what you get. That means Ri is a multiple of n. So this kind of tells you Ri divides. Sorry, not Ri divides. Sorry. Sorry, Ri is the order, right? N is not the order. So n, what you have is n is congruent to 0 mod Ri. So this is what we have. Okay. From here you observe that Ri divides n. So this is same as telling Ri divides n. Okay. So from here I'm writing this statement. Sigma I power n is equal to 1. That means you just use this property. Okay. So a power 1, right? So basically I mod n is equal to 0. Okay. So I mean, the I and n are different here. So this n and this n are different, but from here, if you observe, you will get this particular state. Okay, so that tells you Ri divides n. So in particular, all the Ri divides n. That means what? That means n is a common multiplier of R1, R2, R3. Okay, so n is a common multiplier. That means what? LCM divides n. Because n is a common multiplier and LCM is the least common multiplier, and this is one of the property of LCM. You know that if you have any other multiplier, then the LCM divides that multiplier. Okay, so in particular, what we have proved is the LCM. If you observe, what we actually proved is the following statement. We have proved if the order of a element in Sn, so if you write this sigma in Sn, if you write it as a part of a cyclic in a cyclic decomposition, then this order is nothing but take the length of each of the cycle and take the LCM. Okay, in this case, if you write it as a product like this, so here I did it 3 times. The proof goes exactly the same. Just replace 3 by n. You just write like this. Only the some notation has to come. So this is nothing but LCM of Ri, the set Ri, I equal to 1 to t. Okay. Just take the LCM. So this is actually the interesting part. One of the interesting reason that you want to write it as a part of design cycle. If you don't write it as a part of design cycle, you may not in general get this. For example, suppose if you yeah, one thing is if you don't write it as a part of design cycle, you will not get. Uh, but for example, if you give something like this 1, 2, 3, 4, 5, 6. Okay, which number I missed? Okay. So suppose I say this is my sigma, and I am asking you to find what is the order. See, only easier way you find the order is you just do the sigma multiple times. Now you have a sigma here, then do the sigma square again. So where the 2 maps to 3, 3 maps to 4, 4 maps to 1, and 1 maps to 2, 5 maps to 5, right? 6 maps to 6. And then you just keep on computing things, then you can finally see where the identity comes. That is the way you can do it like this, but it is more computationally hard. But suppose if I write this sigma as, let's say, part of design cycle. Okay, so let me write the sigma first. If I write as part of design cycle, this 1 goes to 2, 2 goes to 3, here 2 goes to 3, 3 goes to 4 again, so 3 goes to 4, 4 goes to 1. Okay, so I closed it. And 5 goes to 5, 6 goes to 6. Okay, so what is the LCM? LCM of the length, this is just a 4, 1, 1. This is nothing but 4. Okay, so you easily computed the order, right? You just take sigma power 4, you got it. That's all. So in that sense, this problem is kind of interesting, because otherwise, it's very hard. Okay, so we have done this, so let's finish up the last problem. I mean, the actual idea is you want to do it without using whatever we are. Okay. So let's do one more problem and then we'll stop. Okay, let's do this one. This problem says the following. Let's P be a prime so that the element of order P in Sn, so an element has order P in Sn if and only if its cyclic decomposition is a product of commuting P cycles. So once you write it as a cyclic decomposition, what you get is a product of P cycles. Okay. Of course, when you write it as a cycle decomposition, it's a disjoint cycle, so it always commutes. If you write it as a cyclic decomposition, that the algorithm that is given in the book. If you write it as a disjoint cycles, then it always commutes. That is not a problem. But what it says is it is the commuting p cycles. Okay. So how do you prove this? Okay. Suppose let's say I have a sigma, and the sigma I am writing as a sigma 1, sigma 2, sigma 3, sigma 4, etc. Okay. But this is sigmas, these are all cycles. Okay. So these are all a single cycles. I'm writing it's a product of cycles. So basically, this sigma 1 looks like something like a A1, A2 to AR. Okay, just one cycle, it looks like this. I have product of cycles. Now I raise to what we know is let's prove both direction. So first we proved that if and only if the cycle decomposition is a product of commuting p cycles, right? We'll do this. So we assume that this element has order p in SN. So now you go this way. Okay, maybe one can directly do it, but let's use the previous theorem and finish it off. Okay, what is the LCM of this? This LCM of this is basically, sorry, not LCM. The order of sigma is nothing but the LCM of this cycles, right? It's a LCM of, okay, how do you write the length of this? Let me call this the length of sigma I as Ri. Okay. By length, I means if you have something like this, the length is just this R. So how many elements here is the length? Length of R1, R2, R3, R4. Okay. But if this is equal to P, okay, that is what we know. The order is P. So when the order is P, the order is P if and only if all of this divides P, right? So this is true if and only if Ri divides P. That is Ri is either P or 1. 1 we usually does not write it when you write the cyclic decomposition. So that tells you all the Ris has to be P. I mean 1 also, but so when you write it as a part of commuting p cycles, the one cycle this is always we can write another one cycle, but usually we don't usually write this one cycle. We just ignore the one cycle. Okay. So what happens is this one cycle we can ignore. There is no other cycle comes. That is the important. There is no 2 cycle. There is no 3 cycle. Only whatever the prime you have, only that cycle will come here. Okay. So directly we proved it. That's all. So the order is P implies all the Ri's are P are 1, but when you write as a cycle decomposition, this one we don't write it. So all the Ri's are P. So if all the Ri's are P, then your order is nothing but the LCM, which is P. One can directly prove it. It's you can try to prove it directly. So keep it as exercise. So prove it without using the previous proposition. Maybe I'll just write it as theorem. I don't know whether it's a theorem or not. So basically the previous problem, that is what I mean. Here we are using the previous problem, but in the book that which I took, usually I took problem from this book. If you are interested, you can look at this. So this book has a lot of problems. If you want to solve some problems, you can try. Divides limit. Okay. So it's a very nice book. Although I will say it's a little bit easier also. May not be very easy when you do the first course, but later you feel it's not a hard book. But for first course, it's good. Little bit dry and maybe somewhat unmotivating, because there are books which are like too much motivating. Compared to that, you feel it's maybe not too much motivating, but it has a very nice problems. If you want to try the problems, you can try this. But on the other hand, once you kind of get little bit used to do this kind of problems and you're trying to solve it, then you realize all these books which have so much motivation, you sometimes feel they write so many things, but ideally you don't have to write all of this. You could have, sometime you may feel, why this guy is writing so much. You could have just go to the statement. But it's depends on which place you are in. If maybe you are a beginner, then you might need a motivation. But if you're not a beginner and you kind of already know what is going on, then you don't actually need much motivation. Because when you read the problem, for example, you look at this statement. Let's say this statement you are looking at. If you are a beginner, then you may see, okay, this is some random statement. But once you look at it little bit more, then you can understand, okay, this is actually somewhat good statement compared to a statement like this, which is very specific for order P, which is not bad, but compared to a statement like this is actually a little bit more general, and you can see it is a consequence of this. So this statement is a consequence of this. So in that sense, this is a nice statement. So then motivation comes naturally when you start doing the problems, and once you reach a certain level, you can able to see for yourself why these things are important. But if you are a beginner, then probably a book which motivating could be helpful. But I'm not sure how motivating the book is. He, it's it's written clearly, but I'm not sure if you really want motivating, like you want a book like Herstein and all. That's a different story. But it has a lot of problems, and he kind of do all things. So if you want one book which covers almost everything, then this is one of the good book. The problems are good. So I think the theory is half. The problems has a more theory than the theory itself. Not maybe more theory, but the equal amount of theory was comes in the problems. So you can try some problems. For example, uh, this when you do this, right, this is one of the very nice theorem, right? If you look, this is one of the very nice statement, but it is given in the problem. Okay, so the problem also goes like this. He do this problem separately and he will give you a hint. Okay, use this problem, use this problem, you can get it. So in that sense, these problems are not also very hard to solve. If you don't give this hint, then it is not easy. For example, this hint says, okay, I have written a formula right here. This hint is this formula. You say if it commutes, then you can do this. This is one hint. Another hint, this is exercise 10. This is basically the hint that the order of this sigma is nothing but this R1. Okay. So this two hint, he kind of tells you, okay, where to look up. If you don't have that hint, it will be hard. But anyway, we will stop right now, and maybe we'll meet later. If you have any doubts, you can ask. Otherwise, we'll meet later. Okay, if there is no doubts, we will see you later. Bye.